Hi, space explorers! Caroline here. Imagine it's the year 1610 and Galileo, one of history's greatest thinkers, is peering through a revolutionary new invention, the telescope. By this point, Galileo has already stirred controversy by suggesting that Earth isn't the center of the universe. But now, he's about to make another bold claim, this time about the most important celestial object in the sky, the sun. He notices something strange through his telescope lens: dark spots on the sun's surface. For centuries, most people believed the heavens were perfect and unchanging. The sun, as a celestial object, was thought to be flawless, a divine glowing orb. Yet these spots told a different story. Did the sun have moles on it? This discovery shook the world of astronomy, proving that the sun wasn't so perfect after all, but maybe a little more interesting. What do you think these spots are? If you saw an image like this in a telescope, as Galileo did, what would you have thought? Pause and make a prediction. As we go through our lesson today, we'll see what astronomers have learned about the sun in the last 400 years. It turns out that Galileo's discovery was only the beginning. At the heart of the sun is the core, the powerhouse of our star. It's where temperatures reach an unimaginable 15 million degrees Celsius, and the pressure is so intense that atoms of hydrogen are squeezed together to form helium. This process is called nuclear fusion, and the combining of hydrogen to form helium releases an enormous amount of energy. It's why the sun glows so bright and hot. Think of it as the ultimate cosmic engine. We'll dive deeper into how fusion works in a later unit, but for now, just know this: without it, the sun wouldn't shine and we wouldn't be here. Just outside the core, we find the radiative zone. Here, high-energy particles bounce around endlessly, colliding with other particles over and over again. They're generally headed outward toward the surface. But how long does it take for them to escape? Believe it or not, it can take thousands or even millions of years for a single particle to make it out of this layer to the convective zone. The convective zone of the sun is often compared to a gigantic boiling pot, where plasma, the hot electrically charged state of matter found throughout the sun, undergoes constant motion. Plasma in this zone behaves like a fluid, with hot material rising toward the surface as it becomes less dense, then cooling and sinking back down as it loses energy. This cycle of rising and sinking creates massive swirling currents, which help transport energy from the sun's interior to its surface. Can you think of any similar processes on Earth? We would also find convection currents in the Earth's mantle, driving plate tectonics, or in the atmosphere, where warm air rises and cool air descends, creating wind and weather patterns. Then we reach the photosphere, the layer you actually see when you look at the sun. This is what we often think of as the sun's surface, even though the sun doesn't have an actual solid surface. The photosphere is where the light escapes into space, giving the sun its bright, shining glow. But the sun doesn't stop there. Just like Earth, the sun has an atmosphere. Its atmosphere is hard to see, though, because the surface emits so much light that the light from the atmosphere is drowned out. When might we have a chance to spot it? Any ideas? During an eclipse. With the sun's surface blocked out, we can see the reddish chromosphere layer. And even further out is the corona, a halo of superheated plasma that extends millions of kilometers into space. When Galileo looked at the sun through his telescope in the 1600s, he had no idea about the layers underneath its surface. But even the surface, or photosphere, was interesting enough. What were the dark spots he observed on the surface, and what causes them? Fortunately, today's technology has allowed us to gather much more information about them than what Galileo had access to. Oh, and astronomers now have a very technical name for these dark spots. They're called sunspots. Easy to remember, at least. And they can be as big as the Earth. Looking at this map of sunspots, what do you notice about the temperatures you see? Is there a pattern that might explain why these spots are darker than their surroundings? Pause the video for a moment and make a prediction. You may have noticed that the temperature inside sunspots is significantly lower than the temperatures surrounding them on the surface. Not cold enough to need a jacket, of course. There's still many thousands of degrees, but it's all relative. These spots are darker because they're cooler than their surroundings, and they're cooler due to intense magnetic field activity in the convective zone below. Why might a stronger magnetic field make the area above cooler? Let's think about what goes on in the convective zone. Convection currents bring hot plasma to the surface, but when the magnetic field is too strong, the convection currents are blocked, and the area above doesn't receive as much heat, forming sunspots. If you looked through a telescope at the sun today, would you see the same sunspots that Galileo saw? Not a chance. Sunspots are very temporary. However, their numbers don't fluctuate randomly. They follow an 11-year cycle. Why? The sun's magnetic field cycles because the sun's surface spins faster at the equator than at the poles, which twists and tangles the magnetic field until it flips and resets about every 11 years. At the start of the cycle, called solar minimum, sunspots are few and far between. As the cycle progresses, the sun's magnetic field grows stronger and more chaotic, leading to a peak called solar maximum, when sunspots and other solar phenomena are at their most intense. Galileo had no idea what was behind these mysterious spots when he first saw them, but his early observations helped us piece together this cycle over centuries. Today, we use advanced satellites and ground-based observatories to track it in real time. And sunspots aren't the only interesting phenomenon happening on the sun. Do you remember learning about solar wind when we looked at the cause of the auroras on Earth? This steady stream of charged particles comes from the sun's atmosphere. Even though these particles move at speeds around 1,000,000 miles per hour, this is just a gentle breeze compared to the space weather that sometimes gets hurled our way from the sun. When massive loops of plasma tethered to the sun's magnetic field arch high above the surface, they form solar prominences. Sometimes the magnetic energy in these regions becomes so unstable that it releases energy explosively, resulting in a solar flare, a burst of intense light and radiation. In some cases, this instability can also cause a coronal mass ejection, or CME, a massive eruption of charged particles and magnetic fields launched into space. Both solar flares and CMEs can have dramatic effects when directed toward Earth, releasing energy equivalent to millions of volcanic eruptions. If the much gentler form of space weather, solar winds, can cause auroras and occasional mild interferences with technology, what kind of damage do you think is done by solar flares and CMEs? And perhaps, more importantly, do we have any protection from these events here on Earth? Pause the video and make some predictions. Fortunately, Earth's magnetosphere and atmosphere give us a significant amount of protection from these phenomena by deflecting or absorbing dangerous particles and radiation before they can reach the ground. But the geomagnetic storms caused by space weather can still wreak havoc, disrupting satellites, power grids, and even causing blackouts. The most recent solar maximum was in 2024, and you may have noticed an uptick in geomagnetic storm activity during this time. The good news was that beautiful auroras could be seen at much lower latitudes than normal. So, the sun is definitely not the serene, perfect orb that people once thought. Galileo's observation of sunspots paved the way for astronomers to learn more about what goes on inside this raging inferno. And what we've learned doesn't just apply to our sun. Stars across the universe function in exactly the same way. Do you have any idea how many stars are in the universe? What's your guess? Astronomers don't have an exact count, but they estimate there to be around a septillion stars out there. Our sun? It's just one single star in this vast sea of stars. And it's actually quite average. Not too big, not too small. Not too young, not too old. And it lives in the suburbs of an average galaxy. So why do we study it so much and have a whole lesson devoted to it in this course? Well, quite simply, because it's ours. Of all those septillion stars out there in the universe, the sun is the only one close enough to give us significant warmth and light. So it may not be anything special compared to other stars, but it's everything to us. So the sun isn't just any star, it's the foundation of life as we know it, a constant force shaping our world in ways we often take for granted. From Galileo's first discovery of sunspots to our modern understanding of solar phenomena, we've uncovered incredible insights into this cosmic powerhouse. Next time you see the sun in the sky, remember all that's going on below and on its surface. See you next time, Cosmic Explorers!
Hey, hey.